So SLC6A1 is a gene that encodes a GABA aminobutyric acid transporter protein. This protein is responsible for removing the GABA from the synaptic cleft and then repositioning it back into the presynaptic terminals. Mutations in this gene are linked to an early onset autosomal dominant epileptic neurological disease, which causes an intellectual disability. The R479 variant is a single nucleotide variant, one base parallel, which creates a premature stop signal. So this is different than all the other variants because the premature stop signal completely halts how the protein is being made. And you'll see this, how it changes it in the graphs and everything in a little bit. I'll point it out for you. So patients with this mutation experience myoclonic-atonic epilepsy shown by quick myoclonic jerk followed by a lack of tension. It's been shown to emerge in early childhood with delayed development as the major indicator prior to seizures. After seizure onset, most patients show intellectual disability. And then ours is only shown in one patient, and it's a little girl, that's why her poster's pink. But all of her data is a little bit different because it is a stop signal as well. So for our background, we had 255 SLC6A1 mutations found using ClinVar, TopMed, and Genome AD. The R479 protein mutation was listed exclusively on ClinVar, and it only had one patient. This data, along with the data found on all other studied variants, was gathered and relocated onto multiple Excel spreadsheets, and these were prepared by Dr. Prokop. The title in the gene is Solid Carrier Family 6 Member 1, and this explains its function. And it is 4,433 nucleotides long. The R479 mutation is only one base pair long, but it does affect each base pair that occurs after it. The gene is located at position GRCH38.12, and then the cytogenic location, distal band, is the third chromosome, petite arm, and then the location is 25.3 on a 26 scale. So you can see it's zoomed in right here on my figure, and then this is it highlighted, and this is the very end. This is the third arm and third chromosome, and then this is it on all of the chromosomes. Alrighty. The patient's variant is considered pathogenic, and further testing revealed the result of this to be myoclonic-atonic epilepsy due to the stop gain. Amino acid 479 is the first affected, and it consecutively affects the remaining 120 amino acids until the end one is reached at 599. The affected amino acid is arginine, which is pretty large, and it codes for the biosynthesis of protein, so we can imply that the protein is not going to be made properly. So for our data and analysis, we have our 21 codon window table listed over there. It was created by Prokop with all the variants listed. The R479 mutation data was compared to the rest, and most mutations of this gene fall in the synonymous category, which ours would normally, but because of the truncated effect, we are going to place it in the non-synonymous category, which is a point mutation that changes the nucleotide in a way that changes the amino acid completely. If the point mutation codes for a stop codon early enough, the protein will no longer be made and it will cause serious effects. If this is proven true, it will be shown in the Acera model of our protein variant. So on our non-synonymous score, we had a score of 3 on a scale of 0 to 37, which seems low, but the median average was 0 from all the variants, so it's actually pretty high. And then on our next graph over here, so we had our gene blasted with the variant into ClinVar, and then this is what you get, and this is the entire SLC6A1 gene. This is the GAP1 location, and then here is where ours is, and you can see it affects this down, and it's just zoomed in here where you can actually see the nucleotide right there. All right, and then we've got our models. So our first one is our variants. Let's see where we got. Right here, our variants found using ClinVar, TopMed, and Genome AD. The variant was found exclusively on ClinVar. And our variant impact is shown to be at 60 right here, which is normally pretty low, but the stop codon was not known when making these, so we would now think that it would be like way higher. And then that's shown again here, except for we just have the amino acid also affected in it. And you can see it's right here along with the other ones kind of near it, but we do expect it to be more up here now. For our third, we've got our species ORF, and this is of 225 species of SLC6A1 through vertebrates. Codon selection metrics and evolutionary conservation analysis were used to predict how conserved each position is throughout vertebrate evolution. And then this shows a very low motif, which means it's not going to impact the system as much as one of these with a higher motif, but we do think it'll impact more because the stop codon as well. And then our fourth one is a measure of the amplitude of atoms' motion during simulation. This helps make the molecular dynamic simulation of the proteins, which are shown over here. And then this chart shows our protein variants via loss of function site, and this correlates with the ClinVar reference. And then the final one is our global deviation comparison. You've got the wild type in black and the R479, and you see they kind of follow along right up until this 12 nanosecond mark, where you see a larger difference throughout it until the end. And then this is probably due to our protein being located at the end, our mutation at the end of the protein. And then our methods. Our models. So all models were created using the Sarah Dynamic Simulator by Dr. Blair for us. The first model, model 6 over here, is a structural model of SLC6A1 viewed from a cross-section on the membrane. And then we have our section highlighted in red on there for you. The second one, model 7, is the same as model 5, or as model 6, except for all of the affected amino acids are also highlighted since it affects them all the way to the end. And then whenever I get the actual mutant version of this back, we're going to see how it affects this one section that we think will be then gone. And then our figure 8 is a structural protein model of SLC6A1 embedded in the lipid membrane. And when we get our figure back, we will also do that. And it'll be the first time that the R479 variant was ever modeled in a lipid membrane. And our results. So the original predicted variant impact for the data and graphs of medium impact was shown to be incorrect because the truncated effect was not taken into consideration. The low motif predicted in the 225 species ORF was proven incorrect due to the same reasoning. The mutation proves to cause loss of function effects in the protein, however. This mutation is thought to be the cause of the patient's epileptic seizures, and then we have 4 out of 24 alpha helices are affected by the mutation. Both beta sheets are affected, and 1 of 4 rough extracellular regions are affected. There's a total of 80 amino acids affected from the C-terminal end, and then the Sarah dynamic simulation for the mutated R479 protein is incomplete at this time. It's uncertain if the modified protein will remain in the membrane or if the mutation completely halts protein activity. Finally, Sarah modeling took an abnormal amount of time to complete, and this is thought to be the result of a major molecular change in the protein. Okay, does anyone have any questions?